Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on graph theory, lecture number 30, in which I will discuss about card sets. Firstly, we want to know what is card sets in a connected graph. We have, this is graph 1 and the same graph, this is graph 2. Here, this is a connected graph. We have here 6 vertices and 8 edges. In the second graph also same, 6 vertices and 8 edges. Two graphs are same. Only we have drawn this graph for making the card sets. If we delete E1, E3, E4, E6, we cut these edges. E1 edge, we remove. E1 edge, E3 edge, E4 edge and E6 edge. Then what will we get? The resulting figure. Here E1 is removed, E3 is removed, E4 is removed and E6 is removed. These edges are removed. Then we get a disconnected graph. Here we get two components. The collection of edges which are removed from the connected graph and makes the graph disconnected, and that collection is a card set. But we have some conditions also. Here collection of edges which have already been removed, be edges E1, E3, E4 and E6. Now again we draw this figure and again we remove some edges so that we may get the graph disconnected. Now edges E1, E3 and E8 are removed from the graph. Then we will get a disconnected graph. Like this. Here two components. Here one component and here another component. In this case, we get a set of edges E1, E3 and E8 which are removed from the graph to get a disconnected graph. If we remove the edge E4 also, then we will get a set of edges E1, E3, E8 and E4. As this set E1, E3, E8 is proper subset of this set. So this set may not be a cut set. We take collection of some edges which are removed from the graph such that they make the graph disconnected. But if proper subset of that collection also makes the graph disconnected, then this set may not be a cut set, and in this case this set will be cut set. So now we define the cut set of a graph. A cut set S of a connected graph G is a minimal set of edges whose removal from G disconnects the graph G. Here term is minimal set of edges. We have to stress on this word, minimal set of edges. So we may define in another way. A cut set of a connected graph G is a set of edges whose removal from graph G makes graph G disconnected, and removal of no proper subset of the set of these edges disconnects G. Here we have seen that removal of edges E1, E3, E8, E4 disconnects the graph also, but proper subset of this set is a set containing edges E1, E3, E8 disconnects the graph, and we have got the graph, disconnected graph like this. This is E4. This is due to the removal of edges E1, E3 and E8. Also these edges E1, E3, E8 and E4, by removing these edges we get disconnected graph, but proper subset of this set also gives disconnected graph. So this set may not be cut set. Minimal set, here minimal set of edges is the set containing edges E1, E3 and E8, and this is the cut set. We may call these as S, and this is not cut set. We may also get some other cut sets as the set containing edges E1, E2, E7. Also we may get here E1, E2, E5, E6. We know that the rank of a graph is n minus k. This is rank. For connected graph, rank equal to n minus 1. But cut set will disconnect graph into two components. So here number of components for a connected graph is 1, k equal to 1. By using cut set, rank of the graph will be n minus 2. That is, rank is reduced by 1. Therefore, rank is reduced by 1. So, we may also define cut set as follow. A cut set is a minimal set of edges in a connected graph whose removal reduces the rank of the graph by 1. Since tree is a connected graph without any circuit, so if we remove one edge from the tree is changed into two disconnected graph. For example, let we have a tree. Here V1, V2, V3, V4, V5, V6 and edges are E1, E2, E3, E4 and E5. If we delete or remove one edge here, we get two disconnected graphs. So each edge of the tree is a cut set. Now we prove a theorem. Theorem is every cut set in a connected graph G contains at least one branch of every spanning tree of graph G. Now we prove this. Let G be a connected graph and T be a spanning tree of graph G. Since spanning tree means the skeleton of the graph G, means T will contain all the vertices of G and T will be a tree. Let S be a cut set of G. That means S be some collections of edges such that removal of these edges makes the graph disconnected. Therefore, removal of S makes the graph G disconnected. If possible, let S does not contain any edge of T. Therefore, G minus S will contain T as a subgraph. Since T contains, T is a spanning tree, so T contains all the vertices of graph G, and since T is a connected graph, so G minus S does not make G disconnected. So we get a contradiction. Hence, the cut set S must contain one edge of T, that is a branch of the spanning tree. Therefore, every cut set in a connected graph must contain at least one branch of every spanning tree. Proved. Now we prove the next theorem. Theorem is any minimal set of edges containing at least one branch of every spanning tree of a connected graph G is a cut set. Now we prove this. Let S equal to a minimal set of edges of a connected graph G such that S contains at least one branch of every spanning tree of G. Therefore, G minus S is a subgraph of graph G which does not contain any spanning tree. Therefore, G minus S is a disconnected graph. Since S is a minimal set of edges of graph G whose removal from G makes G minus S disconnected. Therefore, S is a cut set. Proved. Now we prove the next theorem. Next theorem is every circuit has an even number of edges in common with every cut set. Now we prove this. Let G be a connected graph and C be a circuit of this graph G. Let S be a cut set of G Therefore, G minus S is a disconnected graph with two components. Let V1, capital V1, be the set of vertices of first component and capital V2 be the set of vertices of second component. Let we make a set. This is the set of all vertices of first component, that is the set V1, and this is the set of all vertices of second component. This is the set V2, and let this denotes the cut set S. Since C is a circuit, if all the vertices of C be a subset of V1, means first component. Since C is connected and closed, let us form C inside the set V1. Here we form C. Let this is C. Here no edge of C is common to cut set S. Therefore, number of edges of C and S common to each other equal to 0, which is an even number. Similarly, if all the vertices of C be a subset of V2, second component, then similar to above process, we may say that number of common edges of C and S equal to 0, which is an even number. Now let some vertices of C are members of capital V1 and some vertices are members of capital V2. If we make the circuit C by connecting its vertices we get as follow. Let V1, V2, V3, V4 belong to C. Let V1 vertex belongs to capital V1. So here we take V1, V2 belongs to capital V2. V2 belongs to capital V2. Then we connect V1 to V2 by edge. We connect V1 and V2 by an edge. Let V3 belongs to V2. Let us connect V2, V3. V2 and V3 by an edge. Let V4 belongs to capital V1 here. Now we connect V3 and V4 by an edge. If a circuit is V1, V2, V3, V4, then we connect V4, V1 by an edge. Here we see that two edges E1 and E2 E1 and E2 of circuit be common with cut set S. If V4 and V1 are not connected, then we take another vertex in V2. Here this is V5, and again we return back to V1 because we have to make the circuit is closed. If we connect V1 and V2 by an edge and then we connect another vertex by edge, but lastly we have to return back to V1, and in this process we get in every time two edges. Therefore, these edges of circuit C are common to cut set S. Means, therefore, number of common edges of circuit and cut set be even number. If V4 and V1 are not connected by edge, we draw another edge which connects V4 and V5. V5 belongs to capital V2. And similarly, we proceed to connect with V1 because circuit C is closed. And we get pair of edges of C common to S in every time. Therefore, number of common edges of circuit C and cut set S is an even number. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.